Yeah, thanks. So this one is, so this lecture is the most important one. So like the first two were warm-up for this lecture, and the next two are applications of this lecture. So this is really the most important one. So let me just briefly, before we get into mirror descent, remind you what we're trying to do. So let's see, what are we trying to do? So we have X, which is a finite metric space. And we're going to be considering now this metrical task system problem, or the finite case where you have cost functions. So we're going to have continuous time cost function, as I was explaining yesterday. So CT is a map from X to R plus bar. Okay, so this is a cost function. And maybe I will use the other black pen if it's around. Yeah, so this is a cost function. And remember, what we want is to have a randomized algorithm. So we want to take a random state, and then we're going to pay the cost function, and then we pay a movement when we get to a new state. So instead of talking about random state, now we're going to want to talk about continuous space strategy. So we're going to talk about the probability distribution itself. Okay, so what is the bar? The bar just means that infinity is in the set. Yeah, I just mean so that you can really say, okay, you cannot be there. Yeah. Okay, so now what we're going to choose, we choose a probability distribution. Okay, so instead of choosing a random state, now we're going to talk about choosing the distribution itself. And as yesterday, for continuous space variable, I use the notation x. So x of t is a point in the n-dimensional, n-1 dimensional simplex, which I denote by delta n. So what is this? This is a set of point x in R plus n, such that the sum of the xi is equal to 1. Right? It's just a probability distribution. Very good. So if I choose a random state according to this probability distribution, what is my expected cost? Well, my expected cost is just going to be the expectation of CT at rho when rho is sampled from xt. Okay, so again, my cost, expected cost. This is just the expectation when I sample rho from x of t of CT of rho. But in fact, I will want to view this. This is a linear function of x of t. Okay? So x of t, I view it as a vector. So now I'm going to view CT also as a vector. Okay? So I have n point. For each point, I have a cost. So I view this just, if you want, this is a definition, as the inner product between CT and xt. Yeah?
Yesterday we saw that x was part of the metric space. Now x will be in the complex set.
Yeah, x is not in the metric space. X is a vector. It's an n-dimensional vector.
Yeah, okay.
What is in the metric space is rho, the samples from x. Okay, I just identify x. I just label the vertices, I mean the element, it's 1 up to n. Okay. Good? So that makes sense? So now you see, yesterday we were talking about a convex cost function. Now you see that in this problem, in fact, you have a linear cost function. Okay, and you're choosing a probability vector. Now what about the movement in this model? What is a movement? So what is a movement? So now I need to introduce a crucial definition, very, very important, which is a Wasserstein distance, or the Earth mover distance if you're in computer science. So the Wasserstein distance, the W1 between P and Q, Okay, so P and Q are two probability distributions on the same space, on the metric space X, supported on the metric space X. W1 between P and Q, this is the following definition. It's the infimum over all pairs of random variable x, y, such that x has distribution P and y has distribution Q. Okay, so I look at all the ways in which I can couple the distribution P and Q. So again, P is a distribution on my metric space. Q is another distribution on my metric space. So when I get two samples, one from P, one from Q, these are at different points in the metric space. And I'm going to try to couple them to have a joint distribution so that they are as close as possible. So I want to minimize the expectation of the distance between X and Y. Okay, and we're going to see examples of this Wasserstein distance. In general, it's a pretty complicated object, but in the metric space that we're going to look at, it will be simple for trees. Okay, so does the definition make sense of the Wasserstein distance?
The distance is the finite metric space, oh
yeah. Yeah. So here this is a general definition, but for us we're in a finite metric space.
The distance is from where it's taken?
This is a distance. So these are distributions P and Q on the metric space X. Okay, so these are distribution on X, supported on X. Yeah.
Can you use the marker?
Oh, yeah. Thanks. Yes. All right. So this is the Wasserstein distance. So really, when I will, so xt is a distribution at time t, but I didn't tell you anything about the correlation between, let's say we were in discrete time, between time t and time t plus 1. Okay, I just told you what the marginals are. But of course, what I'm going to try to do, I'm going to try to couple the samples between time t and time t plus 1 so that they are as close as possible. Yeah.
What is that distance between two variables?
Yeah. So x and y. Yeah. Okay. Maybe let me use. Let me use another name. What am I going to use? Mu and nu. Okay, so mu is sampled from P and nu is sampled from Q, and this is mu and nu. Mu and nu, these are elements of X. So P and Q are distributions supported on X. So when you sample from P and Q, you get elements from the metric space. So this distance is the distance that you have in your finite metric space. Make sense? Yeah.
So you use this W1 to find the distance between two timestamps.
Yeah.
So you have a different distribution for each timestamp.
Yes. Yeah, exactly. So again, what is the problem? We are seeing this continuous time cost path, and we are adapting our distribution as a function of the cost that we're seeing. So we're seeing some more cost in some part of the metric space, so we're going to try to move the mass away from that part of the metric space. And the question is, how do we measure this movement? And so the movement at the level of samples, we will have really the distance between rho t and rho t plus epsilon, where rho t is going to be sampled from xt, and rho t plus epsilon is going to be sampled from xt plus epsilon. Okay, this is roughly what this is the distance that you have in your metric space. And all I'm saying right now is that rho t and rho t plus epsilon, I'm going to couple them. I'm not going to sample independently at each time step. That would be stupid. Okay? So I'm going to couple them as much as possible to make them very close to each other, which means that the distance between rho t and rho t plus epsilon, in expectations, it's going to be the Wasserstein distance. Yeah?
Sorry, but I don't understand why you're taking infimum if you are like integrating over all possibles nu and
I see. So what I mean by this is, so this is a couple of random variables. So it has a joint probability distribution. And all I'm saying is that the marginal of the first one has to be P, and the marginal of the second one has to be Q. Yes, Rosé?
Yeah, so to get some intuition, is there like easy to construct a very tiny example?
Yeah. Okay. Sure. Let me just give an example. So imagine you have a line. This is your metric space, and maybe this is P. Okay, so P is this. Okay, so meaning with probability a half you're here, and with probability a half you're here. And Q is gonna be, maybe this one, just shifted a little bit. Okay, this is Q. Okay, so good. So in P, with 40.5, you are at the very left-hand point, or with 40.5, you are at the very right-hand point. And with Q, you're either one to the right here or one to the left there. Okay, so if you were stupid and you were sampling at time step t from P and at time step t plus 1 from Q independently, you might move a lot. Okay, you might move a ton. But you can couple samples from this. You can say, let me first sample from P. And if I ended up here, then at the next time step, I just move there. And marginally, this is still correct because I'm going to be here. If I look at what happens at this time step, I'm going to be here with probability a half and here with probability a half. Okay? So I have just, if you want, I just use randomness here and I didn't use it here. I just used some randomness here and not there. Okay, does that make sense? Yeah. Okay, good. So this is what we're going to do. By the way, this will all just be in the background. We will not have to think about that. What's going to come out in a minute is that out of this, I'm going to make a norm, and then we're just going to be talking about a norm space, and that's it. We'll forget about all of this. Okay? But this is in the background. It's very, very important to understand. Okay, so now let me add another definition, which is the Wasserstein norm. So for H in R plus, not R plus, for H in Rn such that the sum of the Hi is 0. I'm going to define the Wasserstein norm, the W1 norm of H. This is going to be W1 of, let's say, P plus H versus P. Okay, and here I'm being a tiny bit imprecise, but okay. So all I want to say with this definition is how much does it cost if I have some distribution P and I want to apply a little perturbation of it. I want to change it by H. Okay, so imagine just to clarify, maybe I have a distribution like this. This is my density. Okay, so this is my density on the line. And what I want to do is that maybe I want this point to remove a little bit of mass. I want to do this, and I want to put this mass up here. I want to do that. Okay, so this is my H. My H is I want negative epsilon here and plus epsilon there. Okay, so my H is negative epsilon here and plus epsilon there. And the question is, how much does it cost me to make this modification? Okay, this is an optimal transport problem. All right, we don't have time to do a full course on optimal transport, but these definitions are perfectly valid, and I hope you get some sense of what's going on. But my point is that you have this norm which tells you how much it costs to make a little movement. Yeah?
That's always relative to the distribution P.
Say again?
That's always relative to the distribution P.
Yeah, good. So it's not. So it doesn't matter what is the background distribution P. That's why I was saying I'm a bit imprecise here. You can think P is uniform, and then that H is small enough such that this remains distributions, And then for bigger h, you just use a gauge property of a norm to define it everywhere. That's why I was saying I'm a little bit imprecise. But just think of h as something small. You're trying to make a small perturbation. How much does it cost to make this small perturbation? Now, what is going to be the small perturbation here? So we're in continuous time, and xt is going to have a time derivative. It's going to change in continuous time. So at every time step, we will want to make this little change, this little fluctuation, which is the time derivative of xt. So all we're going to pay is the W1 norm of the derivative of xt.
Sorry, but P plus H is not necessarily a distribution.
Yeah, so that's exactly what I was just saying, is that, yes, P plus H is not necessarily a distribution, so think that P is uniform, and H is small enough so that P plus H is a distribution. And then for bigger H, you just use the gauge property of norms to define it. Okay. All right, so for us, so what is a movement? The answer to this question is it is a norm, the W norm, of the time derivative of xt. Yeah. So the two key things are, this is a movement cost, and this is a service cost. Okay, so now I have reduced everything to choosing a continuous path in the simplex. And I have linear functions, they give me the service cost. And I have a norm, which gives me the movement cost. And that will be the background from now on, until we go to K-server, and then when we go to K-server, I will go through this again. Okay. Good. So now recall the gradient descent idea. So the gradient descent idea was to do the time derivative of x of t would be equal to the negative gradient of the cost function. The cost function now is a linear function, so the gradient is just the cost itself. So this would be equal to minus c of t. Okay, and this is a vectorial equation, right? It means that at location I, the speed at which I decrease is exactly the cost. This doesn't make sense. This doesn't make any sense. Okay? First of all, it doesn't preserve the fact that xt is a probability distribution. Okay, if the total mass was 1, I start decreasing everywhere. Okay, it's not going to remain mass 1. Also, it doesn't really make sense because I'm using the Euclidean geometry. Recall, where is this coming from? Recall, this is like in discrete time. In discrete time, the equation would be xt is xt minus 1 minus some step size eta times the cost, which we saw yesterday, the same thing as minimizing the linear function eta ct dot x plus a penalty for moving away from xt minus 1. And the penalty for moving away was just the Euclidean norm squared. Okay, so this continuous time equation, we just derived it as a continuous time limit of this discrete time gradient descent. And this discrete time gradient descent, you see that Euclidean geometry is here. The Euclidean geometry doesn't particularly make sense when you're moving with probability distributions. Okay? And again, we saw that one of the problems was that anyways, this was moving too much. We were not able to control the movement. And we mentioned that maybe with something like multiplicative weights, where there would be an xt here, we will be able to do something. So let me already write the type of dynamics that we're going to look at, and then I explain how to derive them with mirror descent. So the correct type of dynamics are going to be of the following form. They are going to be of the form, the time derivative of xt is in fact, let's say at location I, this is in fact minus ci of t, the cost, but we weighted by the current mass there. plus there will be some other term to maintain that this is a probability distribution, plus some mu t. So this is to remain a probability. And this is a multiplicative weight type strategy. Multiplicative weight type strategy. So you see, it's close to this gradient descent, but there is this crucial change that you're reweighting things. And this will be great, because now what's going to happen is that your movement, notice this is the service cost. This is the expected cost, right? Because this is nothing but the sum over I from 1 to n of CIT XIT, right? So your movement is now going to be related to your service cost. But the service cost itself, as we said with gradient descent type strategy, it is automatically controlled using the potential that we talked about yesterday. So that's what we're going to do now. I'm going to explain why you can view this as a gradient descent. I'm going to explain why in this general gradient descent you still always have the service cost controlled. And then we're going to do a little calculation to control the movement cost. And then we will be done for metrical task system in some simple cases. That's the plan. Is there a question? Yeah?
That
Mu, yeah?
It's not the same one from here. Right?
No,
It's not
sorry.
A probability distribution.
No.
Is it a constant?
This is yes. We're going to talk a lot about that guy. This is a Lagrange multiplier that comes from the constraint that the sum of the xi is 1. And it's very important, and yeah, we're going to talk about it.
Does it also have an index?
No, it doesn't have an index. That's the key, is that it's some uniform force that applies to everything to maintain it to be 1. If you want, yeah, maybe I stop on this for now, and because we're gonna explain it in details. But yes, there's no index I. Okay, so now let's finally talk about mirror descent. So, mirror descent. Or in fact, it's really Riemannian gradient descent. Okay, so I'm going to generalize a little bit the discussion. And instead of moving a point in the simplex, I'm going to move a point in a convex body. Okay, so fix K in R capital N, a convex body. Okay, and from now, just think that K is a simplex. We'll see later today why it's useful to have a potentially more general state space. There will be a good reason for this. So I want to fix this, and with a norm on Rn. So this norm is just going to be the W1 norm eventually in our application. It's going to be the Wasserstein norm. And again, we will be very concrete about what is the Wasserstein norm in the metric space that we consider. But for now, this is abstract. We have a general convex body and a general norm. So now, let me think how I want to explain this. So is there a question? No. So we equip K with a Riemannian structure, and I will explain what this is. So a Riemannian manifold structure just means that at every point there is going to be an inner product, and the inner product is changing with the point. Okay, so it means that, in fact, at every point I'm going to have a matrix that depends on the point, and this is how things are going to be rescaled. And this matrix is going to be a Hessian manifold. It's going to come from the Hessian of some function. Okay, so with a Riemannian structure, derived from the Hessian of a convex function phi, which goes from k to r. Okay, so we're gonna fix this function. So this function, I'm gonna call it a mirror map. This is a mirror map. Okay, so this is your choice. You design the mirror map. You can choose a function. And then what I mean is that for any x in K, there is going to be an inner product. Okay, so an inner product between two vectors. And the inner product is indexed by x. And what this is just the Hessian of phi at x applied to those vectors. Okay, so again, if you want, you can think that you have the convex set, and at every point there is a tangent space. What is a tangent space? It's in fact all of Rn. Okay, it's a trivial tangent space, and the inner product on that tangent space is given by this formula.
Okay. So the application is just multiplying on the left and on the right.
Yes. Yeah, exactly. Yeah, I view this as a, sure. Here I view it as a bilinear map, but yeah, you're correct. You can view it as multiply on the left and multiply on the right. Yeah. I'm going to be more concrete in a minute. Okay, so now once you have this, you can start to do gradient descent where you replace the Euclidean structure by this Riemannian structure. So instead of talking about the Euclidean distance here, the Euclidean distance squared, you can talk about the distance in the manifold. Yeah?
What's the operation?
Yeah, so say here is the norm, the local norm of a vector at x. This is just h transpose Hessian phi at x times h and square root of that. Okay, this is the same thing. Yeah. Okay, so now mirror descent, and I won't explain where the name comes from. So mirror descent goes like this. In discrete time, you will want to say that xt is going to be, let me think, I want to say, is going to be the argmin of some learning rate eta ct, inner product with x, plus 1/2 of the distance in the manifold M. So we keep M with a Riemannian structure M. So the distance in the manifold M squared between x and xt minus 1. And you want to take the minimum for x in K. This, I believe, to me, is a fairly natural formula to write. Okay, so this is just a generalization of gradient descent. In particular, you obtain gradient descent if you take phi to be the Euclidean norm squared. Because, if you differentiate twice the Euclidean norm squared, the Hessian is just the identity. So if the Hessian is the identity, then this norm is just the Euclidean norm everywhere. So then you recover gradient descent when you take the mirror map to be the Euclidean norm squared. But you have much more flexibility now. Yeah, question?
That distance is the one that we can write the norm?
Yes, so this is the geodesic distance in the manifold. But I'm going to be more concrete than that. Okay. This is still kind of, these formulas that I'm writing right now are for intuition. Eventually I'm going to write a differential equation which is very concrete, and I'm going to say it as a solution and everything. This is just for intuition. Okay, so now this distance is a bit complicated to work with, but locally, this is like the local norm, this local norm between x and xt minus 1. Locally, if phi is not changing too rapidly, then this distance should be very close to the norm between x and xt minus 1. So this should be close to the argmin. Oh,
Sebastian, sorry,
yeah.
I'm lost.
Yeah.
This one.
Okay, yeah, please.
So the norm there, the norm of A that you define there.
Yes.
That changes depending on x.
Yes.
Right? So for a given x, you get a different norm.
Exactly, yeah.
So when you're talking about the distance below, distance in the manifold,
Yes.
so you're taking a specific x or?
No, that's the problem, is that you're not taking a specific x here. You're looking at, the geodesic in this manifold, to go from x to xt minus 1, and you're integrating the local norm of the velocity.
Okay.
But I don't want to work with this. All I'm saying is I think this is natural. Yeah, I think this is natural for the distance in the manifold. But what we're going to do, anyway, we're going to do everything in continuous time. So eventually those distances are going to be very local. And locally, this is not changing. Locally, this is just going to be the local norm at xt minus 1. So yeah, the next formula I write is just this, that it should be roughly like minimizing the linear function ct dot eta ct dot x plus 1/2 of the norm of x minus xt minus 1, and it's just the local norm at xt minus 1. Okay? So locally, these two things should be the same. If eta is small enough and the phi, the mirror map, is smooth enough, these two things should be the same, very close to each other. Okay? So now I'm going to spell out what this exactly means. Okay? So in fact, take xt to be defined like this. Okay?
So when you say locally, you mean between xt and xt minus 1?
Yes.
And that's still discrete time.
This is discrete time, and I'm gonna. This formula is not fun. I mean, you can do it, but it's not fun to take the limit when eta goes to 0 in this formula. I'm gonna write another formula where we will see exactly what happens when you take eta to 0. Okay, when you take a very small step size. Okay, so I'm gonna write what is xt, and for this I'm just gonna use first order optimality condition in this formula. Okay, so let me just remind you, if you have a convex function and you're minimizing it unconstrained, then the minimizer verifies that the gradient is equal to 0. The gradient at this point is equal to 0. You're flat. Okay? Now, when you're minimizing with constraints, you don't get that the gradient is 0, but you get that the gradient is in the normal cone. So let me remind you. So, reminder, if you want to, so the argmin of a convex function f of x over x in k verifies the following. So the negative gradient at x must be in the normal cone of k at x, which is defined as, I remind you this from the first lecture, the set of direction theta in Rn, such that the inner product of theta with y minus x is negative for all y in k. Okay, so let's do a picture again. Good. So this is a normal cone, right? So here I have 90 degrees and here I have 90 degrees. Right, so again, the set of directions, so I am at x, okay? x is some extremal point. And what I want is that I want that for any direction going inside, any direction y, so that in this direction, I want my vector theta to be negatively correlated. I don't want it to have positive correlation. Okay, so why is it? Well, imagine that minus grad f had a positive correlation with something going inside. So if minus grad f has a positive correlation with something going inside, I could follow that direction and I would lower the function. I would get a lower value. So this wouldn't be the minimum. So the only way to be the minimum is that the minus gradient is negatively correlated with any direction moving inside the body. Okay. This is going to be a very important object from now on. So I'm going to spend a little bit more time to explain again what this is. But this already should be clear, and this is true. So now, what do we verify here? Okay, so in particular, what do we get? We get the following. So what is another way maybe to put it is that grad f of x plus, let me think, plus lambda is equal to 0, where lambda is in nk of x. Okay, so this is how I want to think about constraint optimization, is that it's not that the gradient is equal to 0, is that the gradient plus a vector in the normal cone is equal to 0. Right? I mean, the fact that minus grad f is in the normal cone, it means that minus grad f is equal to some lambda. So grad f plus lambda is equal to 0. Okay, so, and this term is the Lagrangian. This is a Lagrangian. Okay, so when you do constraint optimization, you don't just have the gradient, you also have a Lagrangian. And for us, it's going to be very, in everything we're going to talk about, K-server metrical task system, this Lagrangian, which is going to come from the constraint, is going to induce some movement, and we'll have to understand very precisely what's happening with that. So it's a very important term. Okay, so let's see what this means for our equation here. So what do we get? We get, so I need to take the gradient of this. So the gradient of this is, it's pretty easy. I get eta ct, that's the gradient of the linear function. Now this one, I will get, this local norm is just the Hessian applied to this. So when I differentiate with the square, the 2, they go away, and I just get the Hessian applied to that. So I get plus the Hessian phi at xt minus 1 applied to x minus xt minus 1 plus some lambda t. This is equal to 0, where lambda t is in the normal cone of k at xt minus 1. Okay. So this is now this is a nice formula where we understand what's going to happen. So now again we want to derive the continuous time limit. So I'm just going to normalize by 1 over eta. Yeah, no? I'm just going to normalize by 1 over eta and take the limit as eta goes to 0. Sorry, and this is xt by the way. Normalize by 1 over eta and take the limit as eta goes to 0. So you see xt minus 1 over eta, when eta goes to 0, this is exactly the time derivative. So I will get ct plus the Hessian applied to the time derivative plus a Lagrange multiplier is equal to 0. So this is going to be the definition of mirror descent. So definition slash theorem. And this is in our joint work. So Michael Cohen, James Lee, Yin Tat Lee, and Alexander Madry. The definition is like this. The time derivative of xt is equal to, so again, this is going to be the time derivative. So I will put ct on the other side, lambda t on the other side, and I will put the Hessian inverse on the other side. So it's equal to minus the Hessian inverse of phi at xt applied to ct plus lambda t, where lambda t is in the normal cone of k at xt. This is mirror descent. Okay. So you see, if the Hessian was just the identity, then we would exactly get the time derivative is minus the cost plus something. But now we have this Hessian term. Yeah. Okay.
So you're just rescaling lambda. It doesn't matter because the normal cone.
Yeah. Good. Very good. So it's not that it doesn't matter. And I was careful to say this is a definition. So I didn't say you get this from that. Okay. So this is the definition. Intuitively, you get it from there. But then you need to prove that, in fact, this is well defined. So this type of equation, you see, it's not really a differential equation because there is this set thing, this set valued thing. So this is called a differential inclusion. So I'm not telling you what the derivative, what the velocity is. I'm telling you the velocity is in some set. Okay, but in fact there is a lot of work on differential inclusions, which is, funnily enough, related to selector theorems, so measurable selection, but for just reason which has nothing to do with this course. But the point is that there is, under mild regularity assumptions, which I'm not going to spell out, but they are going to be verified for everything we do, this differential inclusion admits a unique solution. So that's the kind of funny part, is that, I'm not telling you exactly what the velocity is, but in fact, the solution is going to be unique. And I can explain to you maybe offline why it's unique. So this differential inclusion admits a unique, absolutely continuous, and don't worry about those words, we're not going to use it. So absolutely continuous is just that it's well-defined solution. Okay. So now, this is an algorithm, okay, for our problem. Fix a mirror map phi, take k to on the simplex, take k to be the simplex, and run these dynamics. Okay, by definition, it's going to stay in the simplex. Something is going to happen. Okay, and the question is there a way to generalize the discussion that we were having yesterday about gradient descent and the analysis with the potential, which is the Euclidean norm squared, to this setting? And the answer is yes, and in a very, very beautiful way. So yeah, let me do that now. Okay, so potential analysis. And the first part of the potential analysis goes back, so first part, not exactly in this language, but morely, it goes back to Nemirovsky and Yudin. this is a very, very famous book. I think the Russian version is from 79. This is a very famous book that introduced this mirror descent strategy, and in fact that looked at it in continuous time, and they proposed the potentials that we're going to use. So their observation, let me just say that because this is, I think, an insightful observation, is that a formula of this form, x minus grad f of x, this doesn't make sense. It doesn't type check mathematically. This is a primal point, and this is a dual point. Okay, so of course, in finite dimension, everything is isomorphic. The primal and the dual are the same thing. But in general, it just doesn't feel right. Okay, so what those guys proposed is that instead of doing a dual update on the primal, first send the primal point to the dual using the gradient of some other functional. Okay, so this is a mirror map. You send the primal to the dual using the gradient of this function phi, and then you do the gradient update, and now you come back to the primal. You come back to the primal using the gradient of phi inverse, the inverse of the gradient, which for those of you who know about convex analysis is nothing but the gradient of the Fenchel dual. So this is the formula of mirror descent, and maybe as an exercise, show how this formula relates to the one that I wrote over there. Okay, so show that the above formula relates or is the same, relates to the definition we gave. Okay, so this is some differential calculus, but it maybe gives you a different point of view on the problem. Yeah?
Can you write the formula together?
Yes, I didn't plan to make it an exercise at first. But so the formula, so maybe... right, so do it in the case where there is no Lagrange multiplier. Okay, so k is all of Rn. And the formula is, let's say, xt is the gradient of phi inverse. Okay, I'm still not writing big enough. So xt is the gradient of phi inverse applied to the gradient of phi at xt minus 1, and let's say minus ct. Okay, so instead of doing the update in the primal, you first send xt minus 1 to the dual, you do the update in the dual, and then you come back to the primal. Okay, so shows that this formula is the same as the one over there when k is all of Rn. To the definition we gave when k is all of Rn. Okay. All right, so let's do now this potential-based analysis. And the potential is really, really nice. It's what's called the Brakeman Divergence. Okay, so the Brakeman Divergence is the following quantity. So d phi between y and x is just, so think of y as the truth. Okay, so y is the truth. And you're going to evaluate phi at y. This is just the truth. And now you're going to use local information that you have at x to guess what is the truth. What is the local information that you have at x? It's just the function value and the gradient. So what I mean is this is phi of y minus phi of x minus grad phi of x inner product with y minus x. Okay, this is the Brakeman divergence. So y is the truth, you evaluate phi, this is the true value, but you're trying to guess the truth using local information at x. So for instance, we will see when phi is the entropy, the Brakeman divergence becomes the relative entropy. Okay? But we're going to explain that. So now let's see what happens when to the potential d phi of y of t, x of t. Okay, so this is the proposed potential. This is what's going to replace the Euclidean norm squared that we were doing yesterday. Okay. So by the chain rule, I can do this calculation, the time derivative of this, in two steps. I can first fix y and take the derivative when x is moving, and then I can fix x and take the derivative when y is moving. Okay, the cross terms, they only appear in the second order derivative. Okay, so I can, by the chain rule, I'm going to first fix y and only let x move, and then the other way around. So two terms. There will be the time derivative of phi when y is fixed and x is moving, and then there will be the time derivative of phi when y is moving and x is fixed. Okay, and Nemirovsky and Yudin, they were only interested in this term because for them they cared about convex optimization, and in convex optimization there is just a fixed function and there is a fixed optimum, and you want to get to this fixed optimum. But for us, the optimum is changing dynamically, so you also need this term. And this is going to introduce a very interesting twist. Okay, so let's start. These are easy calculations now. Now it's just calculus. So let's do the time derivative of d phi y x of t. Okay. So this one, when I differentiate and y is fixed, this is 0. So I get my first term is phi of x when I differentiate. I mean minus phi of x. So when I differentiate, I get minus grad phi at xt, inner product with the time derivative of xt. This is what the derivative of these guys look like. Now here, again by the chain rule, when I differentiate this inner product, I have first I differentiate the first term times the second one, and then I add the first term times the differentiate of the second term. So let me first add minus grad phi of x times the differential of this one. So I get minus grad phi of x at t, inner product with the differential of the time derivative of y minus x, which is just minus the time derivative of x of t. Okay? And I have a last term, which is the time derivative of this one times y minus x. What is the time derivative of grad phi of x? It's just the Hessian. Okay, so I get minus the Hessian of phi at xt applied to the time derivative of xt, and this is inner product with y minus xt. Okay, so this is just basic calculus. And now here is the beauty. You see the first line I wrote is 0. Everything cancels. This is minus grad phi inner product with derivative of x, and this is plus grad phi inner product with the derivative of x. So I only get the second term. But now, so all of this, gone. And now, grad phi, Hessian of phi applied to the time derivative of x, well, this is exactly what mirror descent is about. Mirror descent is about the Hessian phi applied to the time derivative of x is equal to minus ct plus lambda t. So this minus Hessian phi time derivative of x is just equal to ct plus lambda t. So this is equal to ct plus lambda t inner product with y minus xt. Okay.
So,
Yeah.
so this Brakeman divergence, did it exist before the work by Nemirovsky, or did they just come up exactly to make a formula so that that thing actually fits? Right?
No, I think it existed before, but I'm not sure of the exact history. But it existed before. It was used in convex analysis. I mean, Cristobal, do you?
Brakeman from the 60s, right?
Okay. Do you know why, for what he used it?
I think for sequential projections, like some projection algorithm.
Oh, okay. Yeah, but it does fit very nicely here. that's for sure. But now we're in store for one more surprise. I mean, we're in store for a couple more surprises. This is really nice. So this lambda t is annoying. We don't like it. Okay. This ct.y minus xt, that makes a lot of sense. This is our regret. ct.y is what opt is paying, the service cost of opt, and ct.xt is our service cost. But what is this lambda t? Lambda t is in the normal column. So it's negatively correlated with any direction going inside. Lambda t dot y minus xt, this is the direction going inside. So this is negative, non-positive. So this is smaller than ct inner product with y minus xt. So we find exactly the same formula as what we had for the Euclidean norm squared. Namely, if the service cost of the algorithm is much bigger than the service cost of opt, then this is very negative, and our Brakeman is going down. So if I pay much more than opt, then I'm getting closer to opt as measured through the Brakeman divergence. Okay, this is really nice. And now there is another part of the calculation, which is what happens when y is moving. Okay, the problem is now the Brakeman is not only going down, sometimes it's going up because opt is moving. It's moving from some reason that we don't understand. But what we want to say is that if he makes the Brakeman go up, he has to pay for it in his movement cost. So we want to say the time derivative is upper bounded by the actual movement, the norm of the time derivative of y. Okay? And this is also going to be true. So let's do the other part of the calculation. So this was part one. Second part is the time derivative of phi when y is moving, but x is fixed. So what is that? We get grad phi of y of t, inner product with the time derivative of y of t. And then this is 0, and here in this term we just have minus grad phi of x, inner product with the time derivative of y. And remember, I have fixed a norm on the space. I fixed a norm on the space, and this is the norm that I'm going to use to measure movement. So now let me just use Cauchy-Schwarz. Right? I have the inner product of the gradient with the time derivative of the norm. This is smaller than the norm of this times the dual norm of that. So this is smaller, and I get two terms. So I get twice, let's say, the supremum over z in k of the dual norm of the gradient of phi at z. Oh, thanks. The dual norm of the gradient of phi at z times the norm of the time derivative of y of t. Okay, and this, I'm just going to call this term the Lipschitz constant. This is the Lipschitz constant of phi. Okay, remember, sorry, if you guys in the back can't see, I'm going to write it again. Okay, so what we find, let me just rewrite what we find. So again, the Lipschitz constant of phi I define it to be the supremum over z in K of the dual norm of grad phi of z. You remember the dual norm of H is just the supremum over, let's say, z in the unit ball, so z such that the norm of z is 1 of the inner product between z and H. Right? The dual norm is just the norm that makes Cauchy-Schwarz work. So right now this is abstract, right? We don't understand what is a norm, so we don't know what is a dual norm, but I'm going to make this concrete very soon. So the lemma that we get, okay, what is the lemma that we just proved? Let's put together those two things. So what we showed is the following. So what we showed is the following, that the time derivative of d phi between y of t and x of t, this is upper bounded by ct inner product with y minus xt plus 2 times the Lipschitz constant of phi times the norm of the time derivative of y of t. So when I integrate this, what do I get? And let me put ct.xt on the other side. What do I get? So this implies that the service cost, right, which is nothing but the integral from 0, let's say, up to time t, from 0 to t of ct.xt dt. So the service cost plus the integral of this. So the integral of this is the integral of a derivative. So it's the last term minus the first one. So d phi of y of t, x of t, minus d phi between y of 0 and x of 0. This is upper bounded by what? I get the integral of ct.yt, which is the service cost, the optimal service cost. Okay, so this is the integral from 0 to t of ct.yt dt. Let's say yt is opt. Okay, so our service cost plus this constant is bounded by the service cost of opt plus 2 times the Lipschitz constant of phi times the movement cost of opt. Right, and this is the integral of the norm of the time derivative of yt. So we find that the mirror descent algorithm, for free, for any mirror map, without doing anything, it has a controlled service cost. Its service cost is, let's say, if you take the Lipschitz constant of 5 to be a half, it is 1 competitive. Okay? And this term, for instance, you can assume, depending on the variations that you're interested in, let's say the algorithm and opt, they start at the same location, then y0 and x0 is 0, and this term is non-negative, so then this is just bigger than st. So, for example, if x0 equals y0, and the Lipschitz constant of phi is 1/2, then we get st is bounded by st star plus mt star. That's pretty nice. Right? So the service cost is just automatically bounded. So all that is left now is to understand the movement cost. Okay, is there any question on this? Yeah.
Why are you taking care of the movement of the surface? I mean,
Why? Because I cannot. So the point is, at some point you have to work. Like, this was not work. Everything was automatic, and there is just, this is very general, very abstract. You didn't have to look at anything concrete, and you get this very